So I'm going to tell you about some work I've been doing, some experiments in getting Mathematica to cooperate with the 3D design program. And this is work done jointly with Todd Gehry. Todd Gehry is the created NetLink, which is a critical component in this work. And Todd did all the heavy lifting on the NetLink side. So by way of introduction and to sort of motivate and explain to you why I'm interested in this project in the first place, I want to give you a brief tour of sort of some landmarks in the history of architectural CAD. And so I'm going to show you three things: the egg, a fish, and a bus stop. So this is the egg. This is in Canada and Alberta. And it's an enormous structure. It's 30 feet long. It's 3 stories tall. This egg sits on top of a pole, and it turns in the wind like a wind vane. It was built in 1975, and so the sculptor had this concept, but he didn't know how to actually realize this structure. So he talked to his cousin, who was a dean of an engineering college, who suggested that novel idea in 1975, probably 1973. It was completed in 75. He said we should do the drawings on computer. You know, this is the Bronze Age of computing. It was a novel idea, and so the work fell on Ron Resch, a very talented and creative geometer and professor of computer science at the University of Utah. So he did indeed design the layout with the computer, produce the drawings by computer, and there are a number of firsts here. So this was the first mathematical description of an egg shape, the first practical application of B-splines, and the first instance of where an architectural skin was both designed with the computer and actually manufactured with computer-aided manufacturing. So Ron Resch not only did all the calculation to lay out the geometry, he devised a system where these anodized aluminum tiles could be cut by laser from the data which came out of his design program. And in fact, that system was eventually developed further and was used to cut the tiles on the space shuttle. So now we're going to 1993. This building is significant in that it was not computer-aided design. Anybody who's familiar with this architect will recognize immediately this is a Frank Gehry building. And Frank Gehry was a reluctant pioneer in computer-aided design. So if you look closely, you can see some tip-offs that this wasn't designed by computer. For one, all of the surfaces are singly curved, which means you can take flat materials and easily clad the surface. The cladding itself is this very simple rectilinear grid, which simplifies things. And the surfaces you see are all actually very simple. They're planes. They're sections of cones and cylinders. So all this was done to make this geometry tractable. And the way the Gehry office works is, so Gehry builds these very detailed models of his buildings. And then his team measures them, essentially digitizes them by hand using plumb bobs and who knows what else, and then draws sections through the models, a whole bunch of sections. So this wasn't working very well because, for one, decomposing that geometry into sections actually made the geometry seem more complex than it was. Contractors didn't understand the drawings. They couldn't conceptualize how to build these things. When they made bids, they bid high because they didn't know what it was going to involve to build these things. And Gehry, who was a rare architect who actually tried to stay within his budget, would subsequently make compromises in his designs to stay in the budget. So he reluctantly started investigating other ways than drawings to convey this information. So this is the fish. This was built in 1992 for the Olympic Village in Barcelona. And this was the first experiment in the Gehry office with computer-aided design. So they started the same way they typically worked, which was to make a physical model. But this time, instead of translating it into drawings, they translated it into a computer model. And their first attempt was to use Alias, which is a mesh-based program, which gives a very good visual representation of the model, but it's not useful, they found, for actually doing construction. And the reason is So the meshed-based model approximates the curvilinear surface with planar facets. And you know, the smaller the facets, the better approximation you get. But that was still not sufficient to actually build the thing, to get all of the thousands of connections in here, you know, millimeter precise, so that everything fits together the way it should. So they turned to another industry that had experience actually designing curvilinear surfaces by computer, the aircraft industry, and Dassault Systems, a French company, and their product CATIA. So CATIA is a NURBS-based system. NURBS stands for non-uniform rational B-spline. It's the standard today in computer-aided design for describing arbitrary surface geometry. And so Gehry's office bought a copy of CATIA. They implemented the model in CATIA. And they gave the contractor who was doing the steel work also a license of CATIA. Developed the design in CATIA, sent it off to the fabricator. They fabricated from CATIA. This was a really time-constrained project. They had 6 months from conception to actually getting it built. They succeeded in doing that, and they were within budget. So there was no going back for Gehry. As I said, that last one was the last one they did without computer-aided design. So this is the bus stop. This is in Hanover, Germany. The city commissioned 10 designers and architects to design wild bus stops. This is Gehry's contribution. This was designed entirely with CATIA. There were no drawings. And when it was sent out for bid, the contractor that had worked on the Fish, they sent out a bid that was a third lower than anybody else's, because they knew they were going to get CATIA data to do the fabrication from. So they were way ahead of the game. So here we are 14 years later. CAD has liberated architecture from the rectilinear box, and there's just this explosion of experimentation and new forms, new structural systems, new materials, new methods of manufacture. This is a really exciting time in architecture. And when I see these things, I get very excited, and I want to get my Wolfram language fingers on there and start exploring. But of course, and also I want architects who are doing these things to be able to take advantage of the breadth and the depth of computation in the Wolfram language to do even better exploration. But of course, the problem is Mathematica doesn't have the kind of visual, designerly interface that the designers need to do 3D design, and those programs don't have Mathematica's functionality. So the obvious thing to do is to couple Mathematica and a 3D design program, get them to cooperate in these design tasks. So if you see architecture like this, it's a safe bet that Rhino was used, at least in part of the design. Rhino is a NURBS-based program. It's not an architectural program per se. It's used to design anything that's three-dimensional, like jewelry, cars, packaging, products, aircraft, toys, and architecture. It's made by McNeil and Associates, an interesting company. They cultivate very close relations with their developers, with people that do external development, and they even have their bug list online. You can go see what the status of bugs are. So Rhino is used today in all of the major architecture offices. Frank Gehry now has Rhino along with CATIA. Norman Foster in London has a scripting group. They use Rhino. They also use Mathematica. Zaha Hadid, Renzo Piano, Peter Eisenman, they all use Rhino. And Rhino is very popular and increasingly popular in architectural education. So you know, there's a lot of interesting work being done by students with Rhino. And some of the hot spots of that are the Architectural Association in London, the ETH in Zurich, RPI, lots of places. So one failing of Rhino is that it only works in Windows, so I have to run Windows on my Mac, which I think hurts its circuits. But so this is Rhino here on the left, Mathematica on the right. And luckily for us, Rhino is .NET based. So using NetLink, which Todd developed, is relatively straightforward to get the two to talk to each other. So I'm going to show you 6 examples of, they're just very simple examples, but they give you a flavor of what's possible. And these are things that I'm really interested in pursuing. So the first one is a mesh inspector. So let's open up a document here that has some meshes in it. These, in fact, all came from Mathematica. And I created a mesh inspector in Mathematica. So if I go over here now and select one of these things, I get, tell me how many vertices, give me some information here. And so you can see this one says it's not solid. This one says it has outward normals. This one, this torus, if you notice, it behaves oddly if I rotate. And if I select that, you can see the reason is it has inward normals. It's oriented the wrong way around. So I can not only get into Rhino and get at this information, but the events that are occurring in Rhino can be communicated to Mathematica. That's what makes this inspector work. When I click something different, it says, oh, there's a new selection, the inspector updates and so forth. Okay, we can go the other way. Let's open up a new document here. Except I have to use Windows control keys. Okay, so here is an example of controlling Rhino from Mathematica. I made this little manipulate, which is a box design widget. So you see over on the Rhino side, I've got these sliders connected to this box, right? And I say new box and translate it, new box, translate it, whatever. Right, change the display mode to shaded. Okay, so this kind of thing, I mean, this kind of widget doesn't make a lot of sense in this case. It'd be easier just to go to Rhino and draw boxes. But you can imagine a constrained design environment where you might want to put this kind of interface together in Mathematica. One thing I don't have an example of, but is certainly possible, is only for lack of time, is that you select something in the Rhino document and you get an inspector attached to that selection and you can do things with it. Or you select multiple objects and it generates some geometry based on that, whatever. Okay, so a third way to communicate with Rhino. Rhino is a NURBS-based program. It has a very sophisticated geometry engine in it. Geometry engines are difficult to build. Our computational geometry group is now putting some of that functionality into Mathematica. It's a very difficult problem to make robust geometry code. So, Rhino has this. You can take advantage of it. You can call Rhino's functions as if they were Mathematica functions. So, for example, this is what you do currently in Mathematica to get the union of a ball and a cuboid. You have to describe the union as a region and then discretize it, which zoom in? Oh, okay. You aren't supposed to read anything. Is that okay? No? Okay. So you describe the union, then you discretize it, which means, depending on the resolution, you don't get really clean model. You can do the same thing in Rhino and get very clean geometry. Okay. This is actually, this functionality, doing Boolean operations on 3D meshes is coming to Mathematica. But it's all there in Rhino. You can do this today. There are other kinds of geometry functions you might want to take advantage of. So here's our Stanford bunny mesh. You can offset that mesh in Rhino to make a fat bunny, or inset the mesh to make a skinny bunny. And this is actually, this has many, many facets. It's a very complex mesh. It's instantaneous in Rhino, really. The time is just in transferring the data back and forth between Mathematica. Okay, that's one way of working, is having Mathematica talk to Rhino. The second way is based on Grasshopper. And Grasshopper this is one of the reasons I think that Rhino has been so successful. So Grasshopper is a visual programming language for Rhino. And designers who think visually generally and like to work visually can write code without ever writing lines of code. They just assemble modules and wire them together. And this architecture is open, so you can stick in your own modules. And so these are some Wolfram language-based modules that Todd and I have implemented. So let's make some structure here. So this is a code module, and now I'll make a panel, and I'll say table of cosine t sine t1 with t going from 0 to say 6 pi in steps of 0.1. Okay, and I'll connect this now into that input. And now what's coming out of that output is the result of evaluating that code. It's not Rhino geometry, so I'll take this other module which turns Mathematica lists of coordinates into Rhino points. I'll wire this into there. And boom, I have some Rhino geometry here. Right? So now I'll go back here and say, let's make this a spiral cone by sticking in a T there. And my geometry immediately changes. There's a spiral. Okay. And let's now take this thing and make another one. And make this one a little steeper cone. Okay, now I have two cones nested in each other. Scale it down a little bit. And now I'll make a line component. That's the wrong one. Right. And I'll make lines between the corresponding points. Okay, and then take that, get a loft component, feed the lines into the loft component, and I have a surface here. Okay, so once you get that geometry assembled in Grasshopper, I can come over here and say bake, essentially bakes the geometry into Rhino, turn off this preview here, and now I've got, and now I have geometry in Rhino. So you can work very fluidly with Grasshopper's visual programming language with little snippets of Mathematica code in there to do some unusual geometry kinds of things. Okay, so this is great. What's even greater is what Todd did. So I told Todd, you know what I really want to be able to do is not just deliver sort of a prepackaged set of components, but I want to dream up a component on the fly and send it over to Grasshopper and be able to use it. So this is the secret to working with Todd. You make a note of that on your agenda, and the next morning you check your email, and Todd says, "Oh, I saw this on your agenda, so I implemented it." So
avoiding doing my real work.
Yeah, procrastination, right? So he made a system that actually does that. I mean, normally, if you make a component, you make a Visual Studio, C# files and everything. You have to do a build, and then you put the component in the right place. This is all automated now. So here's an example. This is the complete code here to make a component that will take an arbitrary expression that produces a graphics 3D output and translate that into Rhino geometry. So there's a little auxiliary function. This is the function that actually builds the component. And now it's in Rhino, or it's in Grasshopper, but unfortunately I have to unload Grasshopper and then reload it to get it to pick up that plugin. And if we're lucky, we'll go over here to the Wolfram components, and there's a new component here, right? So now I can say something like make a panel, and then in that panel I'm going to say graphics 3D of sphere. Let's get rid of this and feed that into there, and I should get a sphere over here, right? There it is. Okay, let's get some more interesting geometry. I've prepared some over here. Copy that, go back to the panel, edit that, and put in the new geometry. And instantly you've got new geometry over here on the Rhino side. So this is really great. You can You can be working along, you think, oh gosh, if only I had this component. You can just program it up, throw it into your toolkit, and you've got it in Rhino. Okay, one more example of that. Okay, so I had this code laying around. This takes a surface of revolution and it populates it with spheres with a phylotaxic distribution. So for example, you change the shape here and the spheres redistribute, and then you can change the number of spheres and so forth. So I made a Grasshopper component out of this. Here I'm going to define a little icon image. Oh gosh, I hope my kernel isn't closed. Okay, and now there's a little auxiliary function. I'm going to build another component. That didn't work. Okay, I'm going to cheat. So pretend I just built that component, and now I'm going to, I have the component sitting here, and if it had built, it would have just appeared in here, but I'm going to put it in there by hand. Okay, now let's reload the Grasshopper component. Oh, that was the wrong one. Let's try again. Okay, let's try again. We'll restart Grasshopper. Okay. That's the wrong one. It's going to take me too long to restart Mathematica to get this going again. But what I would have shown you is exactly the same thing, more or less, in Rhino. With the difference between the previous example is you actually have like points wired into the inputs, and then the spiral phylotaxis geometry coming out the other side. And then when you go back and move the points, you have Mathematica in the loop regenerating the surface geometry and invisibly working with your model as you update things. So you can the person that uses that component doesn't need to know that there's Mathematica running at all. It's just a component that they use within their Grasshopper document. My talk disappeared, my gosh. Okay, so so that's what I have to show you with Rhino examples. So I just wrap up with some plans here. So if you're paying close attention, you remember I told you that meshes really don't work well for this kind of thing, and everything I did here was actually meshes. So what I haven't done is make the components that make it possible to get into the NURBS geometry in Rhino and extract the mathematics so that I can work with it in Mathematica. That's not a trivial project, and it's something I'd like to do. So that's number one on my list. The second thing is, as you saw, in order to get the list of points that came out of Mathematica into Rhino, I had a little conversion component. We need to think about how to configure that set of components so that things work smoothly together. You don't have to worry about converting back and forth. And then finally, what I'm really interested in is getting this into the hands of architects and students and seeing what they can do with it. So I'm very interested to hear if there's any interest from the audience, what your ideas are, what you could use it for. So thank you. I'll take questions.